Hello again. This is Math 2115 coming to you from the College of DuPage, and the title of this lecture is Functions. As always, please be an attentive learner while watching this video. By way of introduction to this topic and by way of computer science introduction, we'll talk about 3 examples. First example involves credit card checking to see if there were input errors. So credit cards typically consist of 13, 15, or 16 digits. For example, here is a hypothetical credit card number. The first digit tells you the system. And in this case, the 4 says, oh, this is a Visa card. And the following digits specify other information as the account number and the bank number and so on and so forth. And these things really depend on the type of card. But the last digit, the 7 in this case, is computed from the preceding digits, and it's called a check digit. And the check digit here is 7, and it's computed from those. And this is to identify certain erroneous card numbers. Not all, but it is a very useful thing. It's not a security measure, but rather it helps detect errors such that people misspeak, or they transcribe things improperly, or enter it incorrectly, or so on and so forth. And here is the way the check digit is computed. Or at least on many cards, it has been computed historically this way. So here is the numbers that you see going along the way, and this is before you've computed the check digit. So you have all of these numbers, and you're ending with this 5 right here. Okay, so what you do is starting from the right and skipping the check digit, you double every digit. If the result of doubling is a 2-digit number, you add the digits, and otherwise you use the original digits. The other digits are not modified. And so what happens here, we're doubling every digit, and then we're adding the 2 numbers here to getting a 1. And so you see we end up with this sequence of numbers that's associated with this. Now if we add these digits, we get 73. Adding these digits. And so if the last digit of the sum is 0, the check digit is 0. Otherwise, we subtract the last digit of the sum from 10, and the last digit of the sum was 3. We subtract it from 10, and we get 7. And that's why we put a 7 here. So you can verify the check digit on your card, and this method of calculating a check digit is called the Lun algorithm. It's named after this fellow who invented it while at IBM, and originally it was patented, but now it's public domain and widely used. That's a function though. Given your numbers of input, you get a unique check digit. Here's another example. Hash functions. Suppose that we have cells in a computer memory that are indexed 0 through 10. You see a small example here. Now there are many more locations, but this is as an example that we can deal with. We wish to store and retrieve arbitrary non-negative integers from these cells, and one approach is to use a hash function. So a hash function takes a data item to be stored or retrieved and computes the first choice for the location of the item, where you're going to store it. So for example, for our problem to store a number in, what we're going to do is we're going to say h of n is equal to n mod 11. Now we're going to talk about what mod means in a bit, so this will make sense whenever you review it, or maybe you already know what this means. Okay, and so this is the result, and actually just looking ahead, what this means is you divide by 11 and you take the remainder. Okay, so what happens then is, and the remainder could either be, when you're dividing by 11, is 0 through 10. So you see that's helping you figure out where to put this. And so where do we store 15? Well, if we divide 15 by 11, it goes once, but with a remainder of 4. So this is the remainder. So that gives you the fourth thing, and that's where you would put these numbers that you were storing. Now suppose you want to store now 257. Now 257 mod 11 is 4, And so that means you try to store it at 4, but you say, oh, something's already there. In this case, we say a collision has occurred, and more precisely, a collision occurs whenever the two functions, the hash function of x equal the hash function of y, but x is not the same as y. So to handle collisions, we have what's called a collision resolution policy that's required. And one simple resolution is to find the next highest with 0 assumed to follow 10 unoccupied cell. If we use this collision resolution policy, we would sort 257 at location 6 because that's the next highest one that was unoccupied at the time. Now, likewise, it works the other way. If we want to locate a stored value of n, we say, well, where should it have been? And we start looking there, and if it's not there, we look in the next highest position. And if it's not in that one, we go to the next highest, and so on and so forth. Now, if collisions occur infrequently, and that means you've got plenty of memory, and if one does not occur, it's resolved quickly, then hashing is a very fast way of storing and retrieving data. And as an example, personnel data are frequently stored and retrieved by hashing on an employee identification number. Now, random number generators, or at least we call them random number generators, are used in computer simulations. And this is a very important and growing art form within computer science and engineering. But the truth of the matter is, things aren't random. In fact, the very famous mathematician and computer scientist, John von Neumann, said famously, anyone who attempts to generate random numbers by deterministic means, that means you have an equation, is of course living in a state of sin. You really don't get random numbers if you have a deterministic function for it. But what we do is we generate pseudo-random numbers. They're not really random, but they're not too bad. And so these are used in simulations to simulate random behavior. So a game program or other kinds of analysis programs will do this. Okay, now the method that is usually used to generate pseudo-random numbers is called a linear congruence method. And the method requires 4 integers to be specified. These are the seed values. So we do again start with a modulus. So when we talk about the modulus function, you say, wow, that's used a lot. That's true. So the modulus function m, a multiplier a, the increment called c, and a seed s satisfying. And so s satisfies all of these constraints. So we set x0 equals s, that's the seed number, and then we generate the numbers this way. So x0 is a seed number. To get x1 and the following, we use this recursion relationship. So xn is found by taking a times xn minus 1 plus c, and then we so instead of really having random numbers, we have pseudo-random numbers. And here's the model that often is used to generate them, and it does involve functions, and it's called a linear congruence method. So we start with 4 integers. It's the modulus, the multiplier a, the increment c, and a seed, and the seed is an important element here, and the seed is a number s between there, and then a is a number between there and c. And so you set x0 equal to the seed, and then it grows. So the progression of pseudo-random numbers, and you can see once you know the seed, it's not really random anymore, it's deterministic. But the seed is generated recursively by the formula that x sub n is equal to, and this is a times x to the n minus 1 plus c, and then you take this mod n. Again, it's the modulus n, the remainder after you divide by n. So the formula computes the next pseudo-random number using its immediate predecessor. And here's an example. If m is 11, a is 7, c is 5, and s is the seed is 3. And so x1 ends up being 4, and the next one ends up being 0. And so you could continue doing this, and here's some additional calculations. So much effort has been invested in finding good values for a linear congruence model, and critical simulations are important for aircraft, nuclear research, and so on and so forth. And we use, in practice, very large numbers for the modulus and a. And these are commonly used numbers, and you can see, wow, those are big numbers. And this generates a number of a sequence of 2 to the 31 minus 1, that's a huge number of integers before repeating a value. Okay, so there is another application of functions. And just as a story, a fellow in Quebec won 3 straight games of computer Keno, and he had to choose 19 of 20 numbers correctly in order to do this. The odds were amazingly against this. They thought he cheated, but really what happened is that whenever the power was cut, the random number generator started with the same seed and gave the same sequence of numbers. And so he looked for power outages and was able to do that. Now we are going to define later, although perhaps not next, the floor and the ceiling of a real number. These are functions that you may have encountered before or may not. And this will happen later, not next in the presentation, but we'll have some more definitions first. Okay, if x and y are sets, a function from x to y is a subset of the Cartesian product xy having the property that for each x in x, the front set, there's exactly one y in y, with xy being an element of the function. We sometimes denote a function f from x to y as f colon x to y. The set x is called the domain of f, and the set y is called the codomain of f. And the set y, such that xy is in f, by the way, that's a subset of the codomain y, is called the range of f. Now, if x is an integer and y is a positive integer, here's where we define modulus. We define x mod y to be the remainder when x is divided by y. You've already seen that in 2 of my 3 examples, this was, in fact, maybe in all 3 of my examples, this was the starring function. And so it is a very important function for you to be familiar with. We say a function from x to y is 1 to 1, and sometimes the word is used injective if for all x1, x2 in x, f of x1 equal f of x2, then x1 equals x2. What that means is that each element in the range only has one thing that is being mapped to it. An equivalent way to say is y is an element of the range, there's exactly one in the domain such that f of x equal y. If there were 2 distinct elements, that would be a counterexample. We also talk about a function f from x to y to be onto, or we say sometimes surjective. If for every y in the codomain, or for every y in y, this is not always just the codomain, there exists an x such that f of x equal y. So everything in the range, it's always onto the range, but sometimes it's onto the entire codomain. Now, a function that is both 1 to 1 and onto is called a bijection. Lots of terminology. Now, suppose that a function is 1 to 1 and onto from x to y. That means every element in y, there's only one x pointing to it, and it's 1 to 1, so for everything in y, there's only one x, and for everything in x, because it's a function, there's one in y. So this is a 1 to 1 onto function, and the function that goes the other way, taking the y value back to its predecessor, the x, is called f inverse. Sometimes it's denoted this way as f to minus 1, that is f inverse. We also talk about composition of functions. Let g be a function from x to y, and let f be a function from y to z. Then the composition of f with g, and it's denoted usually with a circle, is a function f circle g of x is the same thing as first we do g of x, and then we do f of x, and it goes from x to z. We can also talk about binary operators, and that means we take 2 elements from a set x and we get something else. So if you're adding 2 numbers, x plus y, from this set, you will get an answer from this set, and that's an example of a binary operator. So you take 2 numbers and add them together. Now, if x is a set of propositions, and this is a different thing, but you see that conjunction, disjunction, implication, and if and only if are binary operators, because you can apply this to any of those, and what you will get is a different proposition. A unary operator operates on a set X, and you only have one thing. So an example of a unary operator that we've talked about already is if you have a set, you can take the complement of the set, where X is something in the power set of U. So that's an example of a unary operation. Another example of a unary operation is if we had the set of propositions. Negation is a unary operator because we get another proposition. Now finally, we're going to define the floor and ceiling functions. The floor of X, and it's denoted this way, and note that the little feet are at the bottom, and that means that's why it's like the floor, so it's the bottom, is the greatest integer less than or equal to X. So you can see if we're between 0 and 1, the greatest integer is what it is itself. But once I get to 1, I jump up here, and it stays at 1 until I get to 2, and it jumps up. So you get this staircase kind of function. Similarly, the ceiling function, denoted this way, and notice that the little feet are on the top, so that is the ceiling function, is the least integer greater than or equal to X. Now it turns out in computer science and the work we're going to do in discrete math, these come up a lot. And so here are the graphs of those. This is the floor function, that is the left graph, and the right graph is over here, and that is the ceiling function. And again, a parentheses means the point is excluded from the graph, and the bracket indicates the point is included. And you've talked about these before, and so you should be aware of what these mean. Here's a problem from your book just to get us used to doing that. And the problem is a proof. It says if n is an odd integer, then prove that this is true. So the ceiling of n squared over 4 is equal to n cubed plus 3 over 4. Well, let's do the proof. N being odd means n looks like 2k plus 1 for k an integer. So I'm just going to take the left-hand side. So I'm going to plug in 2k plus 1, square it. I get this, and divide by 4. Now when I divide by 4, the 4 is going to cancel here and here, so I get k squared. But when I divide 4 into the 1, I get 1/4. But this is the ceiling function, which means you add up, round up, and so this is going to be k squared plus k plus 1. Now the right-hand side over here, again, I'm taking the same value, so I say, okay, so the right-hand side is 2k plus 1 whole squared plus 3 divided by 4. I expand the binomial, getting this, and then I can divide 4, factor the 4 out, and divide 4 into both, and it cancels, and get k squared plus k plus 1. So you see the left-hand side is equal to this, and this is equal to the right-hand side. Therefore, the left-hand side equals the right-hand side, and we have finished the proof. Here is the floor function, and this is kind of an unusual thing, but actually great mathematicians really studied such things as this. People were really interested in the calendar. So the months with Friday the 13th in a year X can be found using the following function. So y is equal to x plus, this is a x minus 1 over 4 floor function, minus x minus 1 over 100 floor function, plus x minus 1 over 400 floor function. And then I take all of this mod 7. Now, what happens though is I will get numbers for y, but the numbers for y, and since it's mod 7, the remainders can go from 0 to 6. But what will happen is, and it does depend on if you're in a leap year or non-leap year, but these are the months that will have Friday the 13th in them. And you see it changes if you're a leap year or if you're not a leap year. And the problem I did was problem 128 from your book. Find the months with Friday the 13th in 2014. So that means you're taking X to be 2014, but you're computing all of these. Okay, and I do ask, is Y a function of X? And I guess we could say on one hand, Y is a function of X, but if you're really talking about what you're getting in the table as the value of the months, you might say, oh, well, you get a set of months. But anyway, is Y a function of X? And we're going to find the months with Friday the 13th in 2040. So X is going to be 2040. We substituted it up here. Okay, and by the way, you do have mod functions and floor functions in Excel and other calculators, and so you certainly can do this. So I start with 2040 and x minus 1 is this. I do the floor functions, I do the calculation, I get before I take the mod, I get 1842, and if you do the mod 7, I find out that this is 1. And so that means from the table, it tells us in what months, and the table, I'm not going to go back there, but the table says that it will happen in January and April, and I think that is all, because leap years are divisible by 4 but not by 100, and so this is not divisible by, it is divisible by 4 but not by 100, so this is this is a leap year. And so you have to look in the leap year column, but you can see, and this is actually the 2040 calendar, that the 13th is more likely to happen on a Friday. And in fact, it can be shown, this is a separate thing, but it can be shown that the 13th is more likely to happen on a Friday than any other day. And I am showing you a little bit of a proof of that. This follows from the Gregorian calendar. Pope spent a lot of time thinking about this. This is Pope Gregory. And the pattern of leap years happens every 400 years. So what you can do is figure out how many possible days happen there, and that's exactly divisible by 7. So there are these many months, and so you actually can do the calculation, and you find that just slightly, but Friday is more likely to end up on the 13th than anything else. Kind of an amazing, fun fact. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and each other. We're all in this together. God bless you all.